Hello everyone. Today we'll be revising what you already know. So I think you have done logistic regression already in regression, but I would like to revise the basics because we are going to need them in the long run. So first of all, what is the difference between logistic regression and your usual linear regression? So let me focus only on simple regression, okay? I mean simple linear regression or logistic regression with just one variable. What is our model for simple linear regression? We say that my y can be modeled as beta naught plus beta 1x plus epsilon, okay? Now, what does it mean? First of all, when we go for simple regression, if I know that relationship between x and y is more or less like a straight line. So either this, that is straight line with a positive slope, or something like this, that is straight line with a negative slope. Okay, so in such cases, so means basically what we do is, initially we draw a scatter plot of xy. We suspect that okay, there is a linear relationship, and then we go and decide that okay, I'm going to fit the linear regression model. Okay, now when do we go for logistic? We go for logistic regression when my y is going to take only two values, 0 and 1. My y doesn't take any value in between or even above 1 or below 0. So my response is binary. This is like a basic criterion. Now what is the problem? I mean, what is the issue if I have binary response? Why can't I still go for regression? First of all, I can't get a scatter. So if I try to plot now x and y, what I am going to get? This is y equal to 0, this is y equal to 1. So I have certain values of x probably which correspond to y equal to 0. So I have some points here. Okay, some points here. I have some points here. And we don't know. I mean, it's a mixture. So even I might have some points here. So even for some higher values of x, I might have y equal to 1. Even for some lower values of x, I might have y equal to 1, and so on. So I don't have really a linear type of scatter. This is one thing. And a more serious problem is yet to come. Suppose, let us say, even then forcefully I fit this model, y equal to beta naught plus beta 1x plus epsilon. Okay. Now, we know that if I go for the least square estimation, my beta naught, beta 1 values can be anything. They can be negative, positive, 0, anything. So far we have not put any constraint on x. X can technically be anything. So y is binary, but x doesn't have to be binary. I mean, x can be binary or x can be any other continuous valued random variable. Okay. So what is going to happen? For some values of x and some values of beta naught, beta 1, I might get some strange values of y. What do I mean by strange? Now normally when I write this regression model, I know that at the back of my mind I have something like this. I have expectation of y given x as beta naught plus beta 1x. Epsilon is the error part. Okay. So if for some values of beta naught, beta 1 and x, if I get y between 0 and 1, it is still acceptable to me, because I know even when my y takes values only 0 and 1, expected value can still be in the interval 0, 1. Right? You know, I mean, when you have a random variable which follows Bernoulli distribution with say success probability p, you know expectation of y is p and p belongs to 0, 1. So if I have some beta naught, beta 1 and x values for which y takes value say 0.6, it's acceptable. I don't have any issue. But I could also have some beta naught, beta 1 and x values for which y turns out to be say minus 1.6, or for which y turns out to be say 2.1. Means unless I put some restriction on beta naught, beta 1 and possibly x, I cannot guarantee that my y is contained between 0 and 1. Okay. So if I want to still proceed with the same regression model, I'll have to put conditions on beta naught, beta 1, and it's not very optimal. I mean, we don't even know what those conditions would look like because there are infinitely many possibilities of beta naught, beta 1 and x. So we don't know how to proceed. Hence people thought that okay, there needs to be a better way to handle this problem. Okay, to get something to be constrained without really putting what do you call, awkward constraints or very tedious constraints in some sense. Okay, so what? So okay, my y is binary, fine. So I know that expectation of y given x, which I can term as success probability, which is a function of x. Okay, so px, it belongs to 0, 1. I need a way to make this constraint removed. Okay, if I can make px take all possible values in R, then maybe I can take use of simple linear regression. Okay, see, most of the times this is how the research works. You don't like something, I mean, you have a problem, you try to modify it in such a way that you can fit it in the existing framework, that you can bring it in the setup where you are familiar. So regression, linear regression is something we are familiar with. So the problem is my px is between 0, 1. That is the problem. If my px can take any value between minus infinity to plus infinity, I can go to the simple linear regression setup and I'm happy because I know everything over there. So is there any way to convert this px to take values from minus infinity to plus infinity? So we go for some sort of transformation. Okay. So okay, from px I cannot go to negative values directly, but if I consider px upon 1 minus px, then I know it can take values between 0 to infinity, because px is between 0, 1, 1 minus px is between 0, 1, and px can be less than 1 minus px or it can be greater than 1 minus px. As a result, sometimes this ratio will be less than 1, sometimes this ratio will be greater than 1. Okay, if you are not convinced, try plotting. So take different px values between 0, 1 and try plotting this. Okay. So now I am in 0 infinity, and from 0 infinity I still want to go one step further. I want to go to minus infinity to infinity because I want to cover negative part also. So if I take log, I will get log of px upon 1 minus px to be between minus infinity to infinity, and this is what we like, right? So because this is the setup in which we are comfortable, and those who do or follow some sort of betting would know that this is known as odds, probability of winning upon probability of not winning. They are known as odds of winning. Okay, so if your odds are 2, it means you are twice more likely to win than to lose. So these are odds, so this becomes log odds, of course. And now that I have something which is between minus infinity to infinity, I can try to model that thing via linear regression. So we write log of px upon 1 minus px as beta naught plus beta 1x plus epsilon. And now I know how to proceed, right? So this is your logistic regression model. Simple logistic. For multiple, we will have small modifications. So what would be the modifications? Just like simple regression to multiple regression, instead of this single term, I would end up having beta 1x1 plus beta 2x2 plus beta pxp. Okay, that's all. Now couple more things. You might have heard of the S-shaped curve or S-shaped function. So from where does it come in? So if suppose these are x values, let me take x to be positive, and then these are px values. So probability of success for different values of x. So generally, so this is 1, this is 0. So if you plot this curve, probability of success versus x, generally the curve takes S shape. What do I mean by that? For the initial changes in x, the increase in success probability is low. Later it increases quite fast, steeply, and towards the end it is again low. See, let us say that x is the number of hours you put in to let us say study. Okay, number of hours you put in to study. So initially, for getting that passing score, you need to you need to struggle. You do need consistent efforts to increase your chances of passing. After that, once you have put in enough efforts, after that it kind of becomes easy. So a very small increase in efforts can actually result in a significant increase in the passing probability. Whereas there is still some chance event here that the paper turns out to be too tough, and if you want to crack even that kind of paper, you'll need lot of efforts. Okay, even in scoring it is similar. Scoring high marks requires too much efforts, whereas scoring something, once you are in a moderate range, once you have done average amount of study, going from 50 to 55 or going from 55 to 60 may not require that much efforts, whereas going from 90 to 95 would require lot of efforts, because there are some difficult questions which would need you to be very good. Okay, so generally the success probability is similar to this. Initially the increase rate is slow, then after you have achieved some ground, the increase is fast, and then later, after going beyond a certain threshold, it is again difficult. Okay, so this is the famous S-shaped curve, and this we already saw is equation for logistic regression. We can still modify it a bit to get into the form where you are familiar. So we said log of px upon 1 minus px is equal to beta naught plus beta 1x. Okay, I'm sorry, we won't have epsilon here because this px is already expectation. Okay, so we won't have epsilon over here. Okay, now log of px upon 1 minus px is this. So I can try to see what is this in terms of px. So px upon 1 minus px becomes e raised to beta naught plus beta 1x. So this becomes px equal to e raised to beta naught plus beta 1x minus px e raised to beta naught plus beta 1x. Okay, so I have px plus px e raised to beta naught plus beta 1x equal to e raised to beta naught plus beta 1x. So I have px to be e raised to beta naught plus beta 1x upon 1 plus e raised to beta naught plus beta 1x. Is it okay? So this curve is actually an S-shaped curve. Okay, you can try plotting this e raised to beta naught plus beta 1x upon 1 plus e raised to beta naught plus beta 1x. If you plot this on y-axis and x on x-axis, you will get that S-shaped curve. Okay, so this is your famous logit transform. Okay, now couple more things. In linear regression, what is my interpretation of beta naught and beta 1? Beta naught is the slope and beta 1 gives you expected change in y for a unit change in x. Means when x goes from x to x plus 1, what is the expected change in y? That is given by beta naught. So beta 1. So beta 1 is expectation of y for x equal to x plus 1 minus expectation of y for x equal to x, right? So what would be the scenario here? So if I have px plus 1, okay, upon px, what do I get? I would get e raised to beta naught plus beta 1 into x plus 1 upon 1 plus e raised to beta naught beta 1x. So if we want to do something similar to that in logistic regression, we will again go here. So because we know the linear regression setup is familiar, so let us try that here. So if I have log of px plus 1 upon 1 minus px plus 1 minus log of px upon 1 minus px, that we know would be beta naught plus beta 1x plus 1 minus beta naught plus beta 1x. Okay, I am simply substituting the formula for log of px upon 1 minus px, nothing else. So this becomes log of px plus 1 upon 1 minus px plus 1 divided by px upon 1 minus px, using the fact that log of a ratio is difference between the logs. So this beta naught gets cancelled, beta 1x will get cancelled, so I am left with simply beta 1. So basically px plus 1 upon 1 minus px plus 1 divided by px upon 1 minus px will be e raised to beta 1. Okay, so the interpretation of beta 1 here is that beta 1 is actually log of odds ratio. Okay, ratio of the odds for the two consecutive values of x. So e raised to beta 1 is actually odds ratio, and odds ratio has a very important place in logistic regression. You know, the typical example that is given for logistic regression is, does smoking cause lung cancer? Yes or no? Okay, so here my x is binary, yes or no, and y is of course binary, yes or no. Let me call 0 1 0 1. So this odds ratio will tell me whether smoking increases the chances of lung cancer. So if you are denoting, smoking as 1, so x equal to 1 means smoking and y equal to 1 means having cancer. That is my terminology. And suppose odds ratio is equal to say 1.5. Then I would be kind of concluding that the odds of getting cancer for a smoker are 1.5 times more than the person who doesn't smoke. But of course, just like we have always been taught, we shouldn't base our conclusions simply on the basis of point estimate. We should look for confidence interval for the odds ratio. Confidence interval for odds ratio, if it is say suppose 1.2 to 1.8, then I can be confident about my prediction. Why? Because this confidence interval doesn't contain 1. 1 is kind of like your H0. That is, the odds ratio remains same for both the values of x. That would mean that there is no change in the probability of getting lung cancer even if a person smokes, if 1 belongs to confidence interval. 1 doesn't belong to confidence interval means if the confidence interval is completely to the right of 1, it means that x equal to 1 is increasing the chances of getting lung cancer. If the confidence interval is completely to the left of 1, it would mean that x equal to 1 is decreasing the chances of getting cancer. Okay. If the interval includes 1, then we would say that the regressor is not significant. So there is no effect of the regressor on response y. Okay. So that's why whenever you give whenever you give odds ratio in logistic regression, it is very important that you give confidence interval as well. Okay. Now, how do you do estimation in logistic regression? Because least square estimation may not yield well because you have complicated functions and you might have to put constraints and so on. So people go for maximum likelihood estimation. and maximum likelihood estimation actually turns out to be quite well here because my y is binary, so I know the distribution. I know that my y is Bernoulli with success probability px. So y follows Bernoulli with success probability px. As a result, it is quite easy for me to write the likelihood. Likelihood would be product over I going from 1 to n pxi raised to yi 1 minus pxi raised to 1 minus yi. And I know the formula for pxi in terms of beta naught beta 1, and of course even if it's multiple logistic I know the form. So log likelihood will become sum over I going from 1 to n yi log pxi plus 1 minus yi log of 1 minus pxi. Okay, and you can then substitute the value of pxi, differentiate with respect to beta naught beta 1. Of course you won't get explicit solutions, but iteratively you can maximize this likelihood and you do get decent estimates of beta naught beta 1 and of course the other coefficients if other regressors are involved. So that's why in logistic the estimation of parameters is done via maximum likelihood and not least squares, because anyway maximum likelihood method would give you better estimate. How would you choose a model? Model selection is done via AIC BIC. AIC is minus 2 log L plus 2k. BIC is minus 2 log L plus k log n, where k is the number of parameters in your model. Log likelihood is, log L is actually the maximum value of the log likelihood. You must have used AIC BIC in regression or time series also. And as you can see, ideally you want to maximize the likelihood, so you would like to minimize AIC and BIC. Okay, you would like to minimize AIC, BIC and choose a model which gives you minimum value of AIC and BIC. The significance of the regressors can be tested via deviance. You have something called null deviance, which depends on likelihood of the saturated model and likelihood of the model with just intercept. Then you have something called residual deviance, which depends on likelihood of the saturated model and likelihood of the current model. Okay, and then you have to take difference between null deviance and residual deviance. So you are kind of determining whether the current model is significantly better than the model with just intercept over it. So you are testing the significance of the regressors in the current model. Okay, and the distribution for that deviance statistic is actually chi-square, because it's kind of like likelihood ratio, chi-square with degrees of freedom equal to p, that is number of regressors. Why number of regressors? Because your current model will have p plus 1 parameters, p for regressors and 1 for intercept, whereas model with simple intercept will have only the intercept. So the difference between the two number of parameters gives you the number of regressors. Okay. So your homework is to figure out what is the exact formula for null deviance, residual deviance and the deviance statistic. Okay. So let me stop here and we'll continue in the next lecture.